I, Dr. Aditi Ved, on behalf of Sri Vaishnav Vidyapeeth Prasthitalayya Fraternity, would heartily like to welcome our speaker for today's session, Dr. Rashmi Sharma, Associate Professor, Sri Vaishnav Institute of Computer Applications, Dr. Uttam Sharma, Coordinator, Udhbhavana 22-23, Head of Institutes and Department of Constituent Institutions of SVVV, faculty members, staff, and dear students. So before beginning the session, let me provide a little introduction to Dr. Rashmi. She is currently working as Associate Professor at Sri Vaishnav Institute of Computer Applications, Sri Vaishnav Vidyapeeth Vishwavidyalaya, Indore. She is a prominent figure in the field of computer science education in India. She has spent the past decade as an assistant professor at the University of Petroleum and Energy Studies in Dehradun. She has finished her Computer Science and Engineering doctorate from JUIT India in December 2010. Her MTech was also in 2010 and MSc in 2008 in Computer Science, which was earned from Rajasthan's Vanasthali University. She also did BSc Honours in Computer Science from the same university in the year 2006. She has also contributed to over 30 international conferences, journals, and edited volumes. Also, 3 of her patents have been made public. Real-time systems, distributed and parallel computing, algorithms, the Internet of Things, and image processing are all areas of study that she is passionate about. So we welcome you, ma'am. Over to you, ma'am.
Just a moment. Thank you, Aditi ma'am, for a nice introduction. Just I want to do a little bit correction in this one.
Yes, yeah, I realized it.
I completed my PhD in December 2014. Yeah, and MTech in 2010. So, okay. So let me share. I don't want to take too much time, so let me share my screen first. I hope this is visible to all.
Yes, ma'am.
Aditi, is it visible?
Yes, ma'am. Yes, ma'am.
Oh, so very good afternoon to all. So today I'll share some. Share some views on real-time distributed systems. Please do correct me if I am wrong somewhere else, okay? And your suggestions are most welcome, please. So in this presentation, I think it is not working. Okay. So these are the outline of presentation. So first we discuss about a real-time distributed system. Actually, what real-time distributed system is, we discuss here, and then about just overview of some scheduling algorithms. And then my research contribution in RTDS will discuss in this information theoretic entropy and the relationship between entropy and RTDS. And then the research extension of my work and the applications of real-time distributed system we discuss. So what is distributed system? As we are aware with this real-time distributed system, basically contain 2 systems. One is real-time system and the second one is distributed system. So if we start with the distributed system first and then merge these 2 systems. So what is distributed system first? Basically, it is a connection or a connectivity of 2 or more than 2 or multiple independent processors that can connect with each other with the help of network. So what we can do, a big, huge problem we can solve with the help of these distributed systems by using divide and conquer method. So basically, we have 2 different types of distributed systems. So one is your tightly coupled system, and another one is loosely coupled system. So as name explained itself, that tightly coupled system means multiple processors or multiple independent units can connect through a single server. Okay, so here multiple processors can communicate their messages, their data with the help of single server. Or another type is here loosely coupled distributed system. Again, the name explains loosely coupled. It means every system has its own local memory and they are connected with another system's local memory. So every system is independent unit and they are connected with each other. So these are the basic two types of distributed system, tightly coupled system and loosely coupled system. So basically in distributed system, what we have multiple systems and each and every system dealing with some processes, some tasks. So if one system has multiple tasks and resources are less, so what they can, like here in this example, in this diagram, we have C1, C2 and Cn, up to Cn processors. So suppose C1 has multiple tasks or multiple processes and C1 is not able to handle the nth task due to the lack of resources. So what we can use, we can apply the context, we can apply the concept of load balancing here. Okay, so we have two approaches to achieve the load balancing. One is task duplication and another one is task migration. So what we can do in task duplication, under task duplication, the task of one processor, it means the duplicate copy of one task of one processor can copy to another processor. And if second processor is able to execute that process first as compared to the destination process, then they can communicate the result of. So that's why in a task duplication, multiple copies of single task can execute on multiple processors. So this can be the drawback or loophole of task duplication, that multiple copies is generating on different processes as well as result also. So they can increase the problem of overloading. So another concept, another approach for load balancing here is task migration. So as name explained, that task migration means we are migrating your system. One processor is migrating its own task to another processor. It is not copying the task. It is migrating the task. So no multiple copies is there on multiple processors. Only single copy is there on single processor, and it helps to reduce the overloading problem. So these are the two approaches that we can use in load balancing achieve in distributed system. So another thing, we have schedulers. Like in distributed systems, again, schedulers are required to schedule the tasks, to schedule the processes. So we have two types of schedulers in distributed systems. One is partition scheduler and another one is global scheduler. So partition scheduler, what does it? Basically schedule the task of its own processor, and it is not allowed to migrate that task to another processor. Like in this example, we have three nodes. Here, interchangeably, we can use the name node in place of processor. So node 1, node 2, node 3, we have three processors in this diagram. So let us say node 1 is not able to execute task A due to lack of resources, due to lack of time. So due to partition scheduler, node 1 is not allowed to migrate this task A to node 2. Okay, so this is the drawback again of partition scheduler, that this scheduler is not give permission to migrate its task to another processor or another node. So in partition scheduler, task is assigned to one processor and will exclusively execute on that processor only. Migration is prohibited here. On the other side, we have global scheduler. As name global, it means we can use this global scheduler on tightly coupled distributed system. Means one global server is there and multiple nodes are connected on that server, through that server. So tasks can come on the server and server will assign those tasks to respective connected processors. So in this diagram, we have three nodes again, node 1, node 2 and node 3, and these three nodes are connected through given processor, given server. So in this server, we have one global queue, and these tasks will scheduled to respective processors with the help of global scheduler. So with the help of global scheduler, we can use here that priority queue. With the help of that priority queue, tasks on highest priority, that priority can decide on the basis of their arrival, first come, first serve, we can say. So on the basis of their priority, tasks will assign to respective processors. But let us say in node 1, if node 1 is not able to execute the assigned task due to whatever reason, like lack of resources, again, so node 1 is allowed to migrate respective tasks to some other processor like node 2 or node 3. So this is the advantage of global scheduler, that migration is allowed here. So this is the these are some basics of distributed system that we are dealing with in real-time distributed system. Now another system in real-time distributed system is the real-time system. As we all are aware with the real-time. What is real time? Basically, that deals with the time. That deals with the time. It means we have some task, and that task has to complete its execution on assigned time. That assigned time called as deadline. Okay, that task should complete its execution by that time. After that time, if logic is correct, but task is not executed on given time, that there is no meaning of that execution. So in real-time task, that task should complete its execution on that time with correct logic. So we get the basic difference between normal task and real time is logic plus time. Logic should be correct and execution of time is also appropriate on the deadline. But in normal task, deadline is not required too much. The logic should be correct logic. So on the basis of that time limits, this real-time system divides into two types. One is soft real-time system and another one is your hard real-time system. Under soft real-time system, this system has flexibility with deadlines. Flexibility with deadlines means if task is not able to meet the deadline. For a very little example here, video game. We generally play the electronic games. It is mentioned also here, video games. And if one player has completed that game in 16 units of time, and this is the target for another player that he or she, that player has to finish that game before or by that 16 units of time. Okay, so let us say second player is not able to complete that game in 16 units of time, and it takes time little bit more, like 18 or 20 minutes of unit of time. So this lateness of time, this delay of time affect the performance of given player, but it is not affecting on his life, or we can say it is not giving us any catastrophic result. Okay, so this is a soft real-time system. Similarly, in web browsing, if we are searching something and browser due to some network issue, it responds a little bit late, but it is not, it is just affecting the performance again, but it is not affecting us. Similarly, that's why it is called a soft real-time system. But in hard real-time system, if single task miss the time limit by nano or microseconds, that can be the case of loss of life. There can be the chance of loss of life. So that comes under hard real-time system. So for example, our spacecrafts, autopilot systems, these all are the best examples of hard real-time systems. So these are some terminologies that generally we use with the real-time systems. Like one is arrival time again. These are some basic concepts of operating system, also basic terminologies, like arrival time, the time at which our process comes into the system for execution. Now, another is worst case execution time, the minimum execution time the respective process need for completion. Another is deadline. By that time, respective task has to finish its execution. Another is waiting time. Waiting time means due to the execution of higher priority tasks or already executing task, another task has to wait. So that time is called as waiting time. Another is your turnaround time. Turnaround time, basically whenever one task starts execution, so how much time that task take during completion, and what is that? Its completion time basically. So that completion time, that completers time is turnaround time. Another is throughput. Throughput basically we use to calculate the efficiency of CPU. Efficiency of CPU means how many number of processes respective CPU is able to execute in given amount of time. So that is called as throughput of given CPU. So another is these are the aperiodic task and periodic task categories of tasks basically. So periodic task means one task repeat itself in a fixed interval of time. If one task come into the system after 2 or 3 milliseconds, then again after 4 milliseconds that system process will arrive in the system. Similarly, next 4 milliseconds, after 4 milliseconds, this process again arrive in the system. Okay, another one is aperiodic task. Like in periodic task, time interval is fixed, but in aperiodic task, that time interval is not fixed. Randomly, any process come in the system. So these are some basic terminologies that we use in real-time systems. So obviously, it is we are dealing with multiple processes. We are dealing with tasks. So scheduling algorithms again are required here. So basically, main scheduling algorithms are earliest deadline first and rate monotonic scheduling algorithms. So these two are the main algorithms that we will discuss in this presentation. Another algorithms are static cycling scheduling, deadline monotonic scheduling, least laxity first, or p-fair scheduling algorithms. These are some more scheduling algorithms that are dealing with real-time tasks. So we start with the earliest deadline first scheduling algorithm. So before starting EDF, just wanted to tell you that the scheduling algorithms of a real-time system are divided into two categories. One is your static priority based, another one is your dynamic priority based. So dynamic priority based, as name explains itself, that dynamism is there. It means the priority of task can change during runtime also. But in static priority category, the priority of task, if assigned at the beginning, so that priority is fixed throughout the execution. It will not be changed due to the arrival of XYZ process. So this is the basic difference between static and dynamic priority. In static, that priority cannot be changed throughout the execution, throughout the process. And in dynamic priority, the task priority can be changed due to the arrival of some other process. So these are the basic difference between static and dynamic priority based algorithm. So EDF is the one of the best example of dynamic priority based algorithm. So in this one, again, that we discussed in previous slide, that deadline is the concept. Deadline means by that time, task has to complete its execution. So on the basis of deadline, we assign the priority to respective task. If two tasks arrive in the system and task 1 priority is 8 millisecond or 8 unit of time, and task 2 deadline is 6 unit of time. Okay, so deadline of task 2 is nearer than the deadline of task 1. Although task 1 arrive in the system first, but the deadline of task 2 is nearer than the task 1. So here the priority of task 2 is greater than the priority of task 1. So on the basis of their deadline, the priority of respective task has been assigned in earliest deadline first. That's why its name is earliest deadline first. Nearer the deadline, higher is the priority. So sufficient and necessary condition here is the utilization factor. The utilization factor, that is CPU utilization, should less than or equal to 1, or we can say 100%. If the respective task increases the utilization of CPU by 100%, so less than or greater than 100%, then task is able to schedule on respective processor. But if the arrival of given task increases the utilization, then that task is not schedulable on given processor. Then there might be need of migration of task, or the task has to wait for its turn. Okay, so these are the necessary conditions. So U is your utilization, that is task utilization, and multiple task utilization we can calculate with the help of its worst case execution time divided by the period of task. So period of task we already discussed, inter-arrival period of given task. Now, due to this dynamic property, EDF is not working well in underloading conditions. Underloading conditions due to its dominoes effect. Because let us say if task 2's priority is higher than task 1, and after task 2, task 3 has arrived, then again task 3's priority is less than greater than task 2. So it means due to arrival of task 1, or we can say that due to arrival of highest priority task 2 is not able to execute properly, and the task arrives in the system after task 2 is not able to execute timely. So it creates a dominoes effect, that is chain reaction. We can say chain reaction. Just because of lateness of one task, that chain has been created till another task. So this effect is called as dominoes effect. So one problem we find out in this EDF is dominoes effect. Another scheduling algorithm of real-time system here is rate monotonic scheduling algorithm. So one good thing here is one utilization bound factor is here. In rate monotonic scheduling algorithm, one utilization bound factor is there. So first of all, it is your fixed priority. It means if under RMS, if we assign the priority of task initially, so that priority of given task is same throughout the process, and it deals with the periodic independent task. Means independent task, if we have task 1, so its execution on the real result of task 1 is not dependent on the result of task 2. So these are two independent tasks. Now here requirement generally we deal with that the deadline of given task is equal to the period of task. If one task arrive in the system after every 4 milliseconds, so that 4 millisecond is the period of given task. Similarly, if we assign task period equals to deadline, so that 4 millisecond is the deadline of given task. That deadline cannot greater than a period, deadline can be less than period. But here the condition is deadline equals to period. And one utilization bound is here. So on basis of this formula, that is n multiplied by 2 raised to power 1 by n minus 1, it decides the upper bound or utilization bound of given processor, bound for CPU utilization. Here n is number of tasks. N is number of tasks. So n, if suppose 6 tasks or 100 tasks arrive in the system, so the value of n here is 100 multiplied by 2 raised to power 1 by 100 minus 1. Whatever result it will give us, that will be the upper bound of that CPU. And on the basis of that CPU foundation, we decide the schedulability and non-schedulability of given task. So these are the conditions, possible outcomes. If any task utilization value is greater than 0 or less than upper bound, then those independent tasks are schedulable. But that is upper bound. Okay, it is not saying we cannot schedule those tasks, but we cannot say anything about those tasks that increases the limit of upper bound. So it is no conclusion. But if task is greater than, if this utilization is greater than 1, it means there can be a chance of overloading, and your rate scheduling algorithm is, that's why it is working well in task is able to execute or not, if able to schedule or not. If it is not schedulable on given processor, then by using task migration, we can migrate given task to another processor. So one RMS is working well in overloading condition, and our EDF is not working well in this condition. So these are about the scheduling algorithms that we are using in real-time systems. Now jointly, real-time system and distributed system made real-time distributed system. Now what type of design we are using, we can say. So we have one server, the name here I am mentioned here, distributed system. So we have multiple real-time uniprocessors, and these are connected with a single server. Okay, so distributed system consists multiple autonomous computers. These all have real-time operating system. Now till this slide, we discuss about the real-time distributed system, that it is a combination of RTS and data distributed system, and how it looks like and how it is working with help of schedulers and all. Now, next one, wanted to discuss about one problem that deal in our research work. One is overloading problem of that earliest deadline first, or generally in distributed system, if multiple tasks arrive in the system and our respective system is not able to handle those tasks, so overloading problem can occur. So what we proposed at that time, that is already completed and published. So that's why I've removed the name here, proposed joint EDF algorithm. Just mention name here is joint EDF RMS scheduling algorithm. What we did, we hybrid these two algorithms. We hybrid these EDF with RMS. Why so? Because EDF is having problem of dominoes effect, and RMS is working well in overloading condition, right? So why dominoes effect occur? Just because of overloading of tasks, and RMS is working well with overloading condition. That's why the combination or hybrid of EDF and RMS working well in overloading condition, overloading case. So in this scheduling algorithm, this is just an overview. First is these two algorithms combined together we are using, and proposed algorithm reduces the dominoes effect. Why? Because RMS is here along with EDF, and it is working well with in overloading condition. And we are using task migration. Task migration use, it means in distributed computing, we are using global scheduler instead of partition scheduler. So task migration is allowed in global scheduler. That's why we have used here distributed global scheduler. So these conditions we have applied when EDF and RMS use together. So these are some, first of all, I want to show you the architecture. These are the architecture. So this one is the global queue, we can say. Global queue, it means one common server. Through this server, these multiple processors are connected with each other. Processor 1, processor 2, up to processor n. And in this server, multiple tasks have arrived. And we are applying here rate, how we join this RMS and EDF, that I'm explaining you here. Now in global queue, that is global queue, it means in server that are dealing with all the tasks that have arrived in the system. We are using this RMS algorithm. What part of RMS we have used here? This upper bound formula. On the basis of this n multiplied by 2 raised to power 1 by n minus 1, we use for upper bound, that decide the upper bound or upper limit of given queue. That limited number of tasks will arrive, and after the distribution of these tasks on given processors, it again allows the arrival of these tasks. So that's why we have applied the RMS scheduler here on these this priority queue. And then on respective processors, we are using the global scheduler, not partition. Because again, if processor 1 is not able to execute some task and migration is not allowed, then task is not able to execute, and again is the deadline. Okay, that's why we have used here global scheduler that allows the migration of tasks. So in this way, we apply these scheduling algorithms. So, so these are the terminologies. One is global task, waiting queue. So all newly arrived periodic independent real-time tasks will arrive on the global queue. Local task queue, it means local task queue of respective processors. Now, earliest deadline first algorithm we are using on respective processors, and task migration policy is applicable on respective processors. So for task migration also, we have given one limit, that is 0.8101. Because I have not mentioned here the references, but on various papers it is mentioned, then your system is working very optimal when it reaches from around 80%. Now 80 to 100% there are chances of overloading. That's why we have fixed the limit of 0.810. That is, we can say 81% also. So now, what is the procedure for migration? So this is the complete architecture that explains the working of given system. Another one is the intercommunication between all processors. So let us say in processor 1, T1 to Tn task has arrived, and the arrival of this task n minus 1 reaches the utilization limit, that is 0.70. Now after arrival of nth task, the CPU utilization of given processor is greater than 0.81. Okay, it means there is a need of task migration, because if this processor accept another task, it reaches the limit of utilization more than 1, and again overloading can occur and task miss the deadline. So 0.81 decide the migration, and a task will migrate to another processor. Okay, now here the processor migration reaches the utilization limit 0.67. Now here this task can execute very easily. So these are the migration scenario. So this is the algo and the flow chart of given joint EDF RMS, but I'm not discussing here the complete algo, just working of given algo we have explained. We have discussed with the help of this diagram. This is just backend or coding part flow chart. So first of all tasks have arrived, and here with the help of rate monotonic scheduling algorithm, RMS algorithm, we have calculated the upper bound limit. After upper bound limit, if task has arrived and that task is greater than upper bound, then we will execute it for another flowchart I will explain you. And if that task is greater than upper bound, then task is not schedulable. The task is not able to schedule. Now, what is one function here? Under one is your randomly we choose the processor for given task. So here, if your task utilization is less than upper bound, then randomly select the processor and the task has been assigned to the given processor. Now here, on the basis of assigned priorities to task, on the basis of earliest deadline first scheduling algorithm. After that, on the that EDF will work here. This is the flow chart. This is the flow chart of earliest deadline first, where one condition has been changed, only this utilization. If utilization is less than equal to 0.810, then task is ready for the execution. But if it is greater than, then migration function will call. Migration function, how migration function will execute? We have execute this function by using sorting. We sort all the processors on the basis of the utilization values and assign tasks to the processor having least utilization. So due to this, I will not say that complete problem has been resolved, but it reduces that overloading issue. And these are some formulas that we have used, that is for average CPU utilization. Now success ratio here means how many tasks has meet the deadline. These are success ratio. And if failure ratio, forgot to mention here, that is 1 minus SR. That is failure ratio. Now tardiness term here is if task miss the deadline, so by how much time it misses the deadline? It means if task deadline is 60 unit of time and task complete its execution on 18 unit of time. So 18 minus 16 is the tardiness, of given task. So only this last one, I will just introduce this thing here because I just wanted to share this thing just because of the dynamic governing parameter. As in previous slides, always mentioned the CPU utilization. Just because on the basis of CPU utilization, we have our respective scheduler has decided the execution of task, scheduling of respective task on the processor or not. So what here we find that if we change that utilization factor with some other parameter, so that utilization called as dynamic governing parameter, because just because of that CPU utilization or task utilization, this dynamism has arrived in the system. Okay, this runtime has arrived in the system, because if system arrive in the system, we check. If task arrive in the system, we check its utilization. If utilization less than, then we execute it. So this is a kind of dynamism that is created with the help of that utilization factor. So what we did here, we try to replace that utilization with information theoretic entropy. we applied entropy concept on this scheduling algorithm. So this is a new thing that we contributed in this RTDS issue, and I am very happy to share this thing that one of the student of that real-time systems lab that is there in the America has worked on this entropy concept and continuously he is in contact with me. So this is his PhD area also. So this new thing I have contributed in this research. That's why information theoretic entropy we can use in place of CPU utilization. So now we'll discuss little introduction, not in detail, like how we can say that entropy can be replaced with utilization. So on information theoretic entropy of real-time distributed system. So first of all, what is information theory? This concept is developed by the Claude E. Shannon. So if we have some information, if we have some signal, if we so how we check that how much amount of information it is, how much amount of signal is using for further operation. So this is a branch of applied mathematics that is applicable on computer science also. So that's why it is called as information theory. Now entropy is basically the uncertainty or confusion. Many mathematical faculties are also here in our in this presentation. So they are well aware with this entropy concept, I know. So entropy is basically called as uncertainty, means information is there, but how much information? This is the called as confusion. This is the called as uncertainty. So it is called as entropy, and we measure that entropy in unit of bits, nets or bands we can say. So generally we use bits here. So this is just an example, like two-sided fair coin we have, and head and tail is there. So what chances are there to have for coming head or tail? 50% chances are there. So Shannon defined this outcome in terms of entropy, that what unit we can give to this information. So that unit is 1 bit we can say. So if we flip that coin, during the flipping of that coin, we are under uncertainty, under confusion. What will be the result? What will be the result? So uncertainty is about the coin flip. That is effectively 0. Okay, because uncertainty is there. Since we know the outcome, what will be the outcome? So we have gained some information, and this information has been quantified by using the answer here is uncertainty. That uncertainty is called as entropy here. So this is the formula of entropy. Probability of given outcome multiplied by information of given probability. So that information has been calculated by 1 divided by log base 2 probability of given information. And the addition of this first probability plus information plus second probability information will give the 1. So these are the information entropy concept that we have used. Now directly I'll come to the relation. First of all, we'll discuss about this thing, how we can apply the entropy concept on our scheduling algorithms. So let us say we have any task that arrive in the system for execution purpose. So if system has arrived in the system, so we have some arrival time. So that arrival time here is 2 units of time, and worst case execution time is 1 unit of time, and this is the deadline, that is 4. So we during execution or during arrival, no system is sure that what is the probability of success. So how we calculate, that is length of successful outcome divided by length of total outcomes. So length of successful outcome means arrival of task in the system plus its worst case execution. How much time that task will take for execution, and divided by its deadline, because its total outcome is 4 units of time. Anyhow, that task has to complete its execution by 4. So that's why the probability of meet here is 0.75 and miss is 1 minus probability, that is 0.25. Now by using this log base 2, we have calculated the task meet information and task miss information. And by using same formula, we have calculated the entropy, probability of meet multiplied by task meet and miss, and in this way we can calculate. So I think for this information theoretic entropy, one separate presentation should be there. Okay, so by using normalized entropy, after the calculation of all these values, we calculated normalized entropy and we calculated the respective CPU utilization and plot one graph. So we can see the green represents the normalized entropy and the blue represent the utilization value of given processor. So it is showing one-to-one mapping. It is showing one-to-one mapping. It means we can use entropy in place of utilization also. Although these two are working well when we execute it, the additional advantage of entropy here is entropy can deal with space also. Not only with time, with space also. Okay, so this is the additional contribution of entropy in a scheduling algorithm. So this is all about the research work. I am not going to discuss all these things because this threshold limit means number of tasks, maximum number of tasks we have in the processor and the calculated maximum entropy. Now, another 5 minutes, quickly I'll explain you the little bit extension of work and its application that can be applicable on multiple fields. Like in research extension, currently I am working on the interconnectivity of given processors. Interconnectivity means networking is there. So we are dealing here with regular type of network, random network, and scale-free. These are three types of nature-based network. So we are dealing with nature-based network connectivity because the connectivity of processors also affect the execution of tasks. If connectivity is not proper, then task execution will take time. But if connectivity is proper, then execution of given task, timely execution of given task will not take too much time, or it can execute on time. Plus, it also helps in fault tolerance concept. If one processor is not able to execute and its connectivity is, its degree of connectivity is more, it means we can transfer that task to another processor. So that's why we have chosen this topic again and we are extending it. So these are some features. With the help of these features, we can choose which type of network is feasible. Resource sharing, openness should be there. Scalability, it means if we want to add some another processor in the system, then we can add. Fault tolerance concept should be there. It means if connectivity is more, then we can easily handle the faults. Transparency should be there. Give which machine or which processor is communicating to with which one. So when routing table concept is there, we can use it. So these are three types of network structures that are using in this work. These are nature-inspired network connectivity, regular, random, and scale-free. So as per our calculations, scale-free structure is working well as compared to regular or random. It was just a calculations on some case studies basis. So we are working on execution part also. Now these are the applications. Just application means where we can apply this real-time operating systems. As we all know, in today's scenario, in today's today's the era of Internet of Things. So Internet of Things means we have the combination interconnectivity between embedded devices, interconnectivity between devices, or embedded devices are also there. So embedded devices means some that can execute one specific application, and 90% embedded system contains real-time operating systems. In real-time operating system means real-time scheduling algorithms are there. So on those real-time scheduling algorithms, we can use this work, whatever we discussed. Okay, so this is called, this is one of the application, or we can use those embedded systems in respective areas like agriculture also. We can implement as per our requirement. We can do some changes. We can create some scheduling algorithms. We can modify some algorithms or use accordingly. So another thing is real-time embedded systems. Here only embedded system means like your AC, our smart refrigerators. We have these are embedded systems. They are dealing with specific applications. But if one smartness is there, smartness means if we apply artificial intelligence on that embedded device, it comes into Internet of Things device. First one is simple embedded system, but if we put intelligence, then that device becomes IoT device. So directly or indirectly, real-time operating system, we can say is a brain or is the best thing that we can work on in aspect of today's era. Now, currently in industries, the revolution is fourth revolution is industry 4.0 right now. So maximum companies are using Internet of Things concept right now. So that's why it is called as IIoT, industrial IoT, and that is industry 4.0. So this is the conclusion of given work. So that joint EDF RMS we have used in RTDS. And to the best of our knowledge as of now, entropy concept are not using. So it has a large scope of research also, because we have done on EDF scheduling algorithms only. We use entropy concept on EDF scheduling only. So right now we are working on joint EDF RMS on various scheduling algorithms also. Another work on optimal network connectivity. And open research areas we have in IoT solutions also. Another one is risk we can discuss, security we can discuss. We can work on the multiple layers of Internet of Things, multiple protocols of Internet of Things or embedded system also. So these all are the basic future scope of real-time distributed systems that we can work on. So thank you very much all for listening all these things, and I feel great if it is required.
Thank you, ma'am.
Thank you so much, ma'am. So now I would like to request our audience if they have any questions for ma'am.
No, ma'am. Thank you for that.
Thank you so much, sir.
So as we come to the end of the session, I would like to request Professor Bhavesh Joshi to propose word of thanks.
मैडम रश्मि मैम, मेरे दो क्वेश्चन है, बेसिक क्वेश्चंस. हेलो.
Yes sir. Yes sir.
जी सर.
एक तो ये बताइए मैडम कि व्हाट इज द कंसेप्चुअल डिफरेंस बिटवीन रियल टाइम P2P सिस्टम एंड रियल टाइम डिस्ट्रीब्यूटेड सिस्टम.
So peer to peer, it means that one machine is directly communicate with a respective machine. That is peer to peer communication. And real time distributed system में आपका basically दोनों चीजें आ जाएगी. Peer to peer भी communicate हो सकता है, and through server भी multiple machines can communicate.
तो वो बेसिक डिफरेंस यही है या और कोई कंसेप्चुअल डिफरेंस है इसमें?
Sir, बाकी conceptual, if we go through, if we communicate these machines, obviously we are communicating these machines with the help of network. So जो network आपका जो layer है, architecture है, उसमें peer to peer communication जो है वो vary कर सकता है. तो sir,
आपका जो proposed algorithm है वो real time P2P पे भी काम करेगा, सपोर्ट करेगा?
हाँ सर, करेगा सर.
तो एक ये वर्क और हो सकता है आपका, इस डायरेक्शन में भी आप इसको थोड़ा एक्सप्लोर करिए, ठीक है?
ओके, श्योर सर, थैंक यू सो मच सर.
दूसरा ये है, व्हाट आर द सिक्योरिटी एस्पेक्ट वी नीड टू कंसीडर फॉर डिस्ट्रीब्यूटेड सिस्टम, स्पेशली रियल टाइम डिस्ट्रीब्यूटेड सिस्टम?
सर स्पेशली फॉर रियल टाइम डिस्ट्रीब्यूटेड सिस्टम, सर उसके एस्पेक्ट में तो मैंने नहीं सोचा, लेकिन हाँ सोचना चाहिए. बट मैंने आईओटी के एस्पेक्ट में जो चल रहा है आजकल वो चीज दिमाग में चल रही है. बट श्योर सर, आरटीडीएस के एस्पेक्ट में सिक्योरिटी का कंसर्न होना चाहिए. यू आर राइट सर. सो
ये दो तीन ऑप्शंस हो रहे हैं जहां आप अपने वर्क को और आगे बढ़ा सकते हैं, ठीक है?
थैंक यू सो मच सर फॉर सजेशंस. आई विल डू इट सर. थैंक यू.
ओके, थैंक यू.
Thank you. So any more questions are there? So I suppose we can end the session with Bhavesh sir's word of thanks. Over to Bhavesh sir.
So good afternoon one and all present here. As we come to the closer of Udhbhavana 2022-23 session 3rd, it's my privilege to propose words of thanks on the behalf of organizing team to all those who helped us in making this session such a resounding success. Firstly, I want to express my gratitude to our speaker of the day, Dr. Rashmi Sharma, for kindly accepting our invitation and gracing the event with her valuable sharing. Thank you, ma'am. I am very grateful to Dr. Upinder Dhar sir, Honorable Vice Chancellor, Shri Vaishnav Vidyapit Vishwavidyalaya Indore, who gave the opportunity to organize this session and for providing us with all the possible supports towards conducting this event. No event can take shape without hard-working leader. It was the dedication and enthusiasm of Udhbhavana coordinator, Dr. Uttam Sharma, who made this event possible in online mode also. I express my heartfelt gratitude towards him for his enormous cooperation and organization of Udhbhavana. Thank you, sir. I acknowledge and thanks the unwavering support received from all the faculty and staff members. And last but not the least, thank you all the participants for being with us and for participating actively in the session. We are looking forward for your future participation. I once again thank you everyone whose contribution has made this session a successful one. Thank you all. Thank you for being with us. I would like to wish you a happy Diwali.
Thank you. Thank you everyone for joining. And with that, we come to the end of our session. A very happy Diwali to everyone.
Happy Diwali to all, ma'am.